Thank you for watching this video. Before I take about 15 minutes to illustrate functions of distance warning and signaling system, or DWSS, I would like to take about 4 minutes to review the concept of the system and how it works. The DWSS system is based on my novel formula, which is WD equals speed of a follow vehicle FV minus 0.8 of the speed of a lead vehicle LV, or any variations of the formula such as the relative speed of the two tailgating vehicles plus 0.25 of the speed of the lead vehicle. In any case, the formula involves only two speed variables relating to the two tailgating vehicles. The value that is calculated by the formula is threshold of actual safe distance between the two tailgating vehicles. When the follow vehicles passes the threshold of the calculated safe distance, which is an actual safe distance between the two tailgating vehicles based on my discussions in my paper by referring to the previous research, this distance will be considered as unsafe when the follow vehicle passes the threshold of the safe distance. And because the system generates warning pulses within the safe distance, the unsafe distance is referred to as warning distance. Now, how it works? Whenever the system realizes from comparison that the calculated value WD or one of its fractions is greater than radar measured distance between the two tailgating vehicles, the system concludes that the follow vehicle has passed one of the thresholds of the warning or unsafe distance, and so the system generates a new time to collision pulse TTC1 or TTC2 or TTC3, which indicates different cruciality of TTC as the follow vehicle enters into different stages of the warning or unsafe distance. With the concept of this invention, the TTC is the amount of time needed by the follow vehicle to travel the calculated warning distance and reach the lead vehicle and collide with it when the lead vehicle brakes very hard to stop. In addition to the TTC pulses, the system uses its speed sampling method to generate distance reduction rate pulses to indicate how fast the follow vehicle is approaching its lead vehicle. When the DWSS system is coupled with backward-looking distance and speed radar sensors, the system sends its TTC pulses and distance reduction rate pulses to a coupled backward-looking driver assistance system, such as a signaling display system on the rear of the lead host vehicle for generating repelling signals of lights for the follow vehicle. When the DWSS system is coupled with forward-looking advanced driver assistance systems, or ADAS, such as AEB system, the DWSS system sends its TTC pulses and distance reduction rate pulses to the forward-looking ADAS system so that the ADAS can use the pulses to decide how to control its host vehicle based on the cruciality of the TTC pulses and the rate at which the distance reduction rate pulses are generated. And finally, I'd like to mention that a vehicle can be equipped with both the forward and backward looking distance warning and signaling system, or DWSS. In both cases, the average of the dynamically calculated TTC is between 2.4 seconds and 3.3 seconds, and the TTC increases as magnitude of the relative speed of the two tailgating vehicles increases, as I explained in my paper. In this prototype, I'm using 3 pulse generators in order to simulate the frequency of pulses from distance and speed radars for generating the speed of the lead vehicle, the relative speed of the two tailgating vehicles, and the relative distance between the two tailgating vehicles. With such examples on the display board of speed of lead vehicle of 80 or approximately 80 km per hour, relative speed of 10 km per hour, we have a calculated threshold of safe distance of 30 meters, and the distance radar is showing the 49-meter distance between the two vehicles. In addition to generating the TTC pulses by using the WD and its fractions, the system also uses 3/2 fraction of the calculated threshold of safe distance WD or warning distance WD in order to generate a pulse for turning on green lights when the follow vehicle passes the threshold of the 3/2 of the warning distance. There are a couple of advantages of the green light. The first thing is that in case that the follow driver is inattentive to its lead vehicle, after it passes the threshold of the 3/2 of the WD, the green light turns on the rear of the lead vehicle in order to grab the attention of the follow vehicle that it is not traveling in the vicinity of the lead vehicle. The second advantage of the green light is that according to the research, change of color from red to green light reduces the perception time of the follow vehicle by approximately 0.4 seconds, and at 100 km per hour the follow vehicle travels about 11 meters during the 0.4 seconds, and that can be deterministic. In order to activate the green lights, I can now reduce the distance between the two vehicles to less than 45 because we have the calculated value WD 30. So if I reduce it, so as soon as the speed goes under 40, the distance, the relative distance goes under 45, the green lights turn on. So as we can see, the green lights are turned on the rear of the lead host vehicle in order to inform a possibly inattentive follow vehicle that it is not traveling in the vicinity of a lead vehicle. If the follow vehicle approaches the lead vehicle with a relative speed until the follow vehicle passes the threshold of the calculated safe distance, then the system turns off the green lights and turns on orange lights. So if I reduce the measured relative distance between the two vehicles to a value that is less than the calculated threshold of the safe distance between the two vehicles, then we should see that the green light, the orange light turns off while the green lights turn off. So the purpose of the orange light on the rear of the lead host vehicle is to inform the follow vehicle that it is now traveling within an unsafe distance from its lead vehicle. If the follow vehicle ignores the warnings of the orange light and continues to approach the lead vehicle so that it passes half of the threshold of the calculated warning distance, then the system flashes the orange light at the rate of 1 Hertz. When the follow vehicle travels within this range of half and a quarter of the calculated value WD, which is the threshold of the safe distance. So if I reduce the measured relative distance to a value which is less than half of the calculated threshold of the safe distance, you should see that the orange light flashes at the rate of 1 Hertz. If the follow vehicle does not pay attention to the flashes of the orange light on the rear of the lead host vehicle and continues to approach the lead vehicle and travel within a critically dangerous distance from its lead vehicle, that is the last quarter of the calculated warning distance, the system generates a third TTC pulse and flashes the orange lights at the rate of 2 Hz as an attempt to repel the follow vehicle. So if I reduce the measured relative distance to less than 1/4 of the calculated value of the safe distance, we can see that the orange lights flash at the rate of 2 Hz. Also, it seems like that the best location for the standard center high-mounted stop lamp is between these two red lights, because they are close to the green lights, and in case that brakes are applied while green lights are on, the change of colors from green to red will be more obvious to the follow vehicle, and the perception time of the follow vehicle is reduced more effectively according to the research. Another point I would like to reiterate is that if the functions of lights or the backward looking distance warning and signaling system, which I illustrated here, are not desirable, then the forward looking distance warning and signaling system can be coupled with the ADAS systems such as AEB, so that the research recommended TTC of the system and the distance reduction rate pulses of the system can be sent to the ADAS system, and the ADAS system decides how to control the motion of the follow vehicle if the driver of the follow vehicle does not react to its distance reductions from its lead vehicle. So here are other examples of speeds and the relative distance and the calculated threshold of the safe distance or the actual safe distance between the two tailgating vehicles. Before showing the flashes of the red lights when the relative speed is increased, I have to mention a couple of points. First, of course, all these values are related together, and when the speed of the lead vehicle is reduced because of braking and the relative speed is increased and the relative distance is reduced, unfortunately I cannot show all these changes simultaneously, but I can separately change the value of the relative speed first. To show the flashes, I can then change the value of the speed of the lead vehicle and the relative speed. Also, these pulse generators are unfortunately basic, and I cannot gradually change the frequency to gradually change the speed and distance as in real-time driving. And I apologize for this limitation here. Also, the flashes of red light when the lead vehicle brakes happen only if the follow vehicle is traveling within the range of the calculated warning distance. This is the same for the green and orange lights, that their functions happen only if the follow vehicle is traveling within the calculated warning distance. This is because we want to prevent the unnecessary illumination and flashes of the lights of the system to maintain the integrity of the lights of the system. Also, something to remember is that when the lead vehicle brakes, the follow vehicle has an average of 0.75 seconds of perception delay before reacting to the braking by the lead vehicle and reducing the speed and increasing its distance. So by having all these things in mind, I will now apply the brake and increase the relative speed. So if the lead vehicle brakes very hard, at 8 meter per square second to reduce speed by some 40 kilometers per hour, then during 5 seconds 8 flashes of the red light should happen, and during this time we can first increase the relative speed, and per every 5 kilometers per hour a flash is supposed to happen. So as I said, unfortunately I cannot precisely control the pulse generator, but I believe that I could show that the flashes can happen per approximately 5 km per hour increase in the speed of the vehicle. The system also includes a non-flashing stop lamp which turns on at the speed of less than 8 km per hour regardless of braking on the host lead vehicle. There are two advantages with such non-flashing stop lamp when speed of the vehicle is under 8 km per hour. One is that when the lead vehicle brakes and the red lights flash to indicate distance reduction rates of the lead vehicle to the follow vehicle, as explained before, the flashes of the red light indicate that the lead vehicle is in motion. When stop lamp is on and does not flash, it indicates that the lead vehicle is stopped or is stopping. The contrast between the flashing and non-flashing of the red light makes it much more obvious to the follow vehicle what is the motion of the lead vehicle, whether the lead vehicle is stopped or is in motion. When brakes are applied, the triangular combination of the brake lights of the vehicle and the stop lamp of the system reassure the follow vehicle that the lead vehicle is totally stopped. When brakes are not applied and the stop lamp is on without flashing, it can inform the follow vehicle that the lead vehicle is stopping. Thank you for watching this video. After making the electronics specifications of distance warning system ready, I constructed the system on a prototyping breadboard as soon as I could to illustrate the feasibility and functionality of electronics of the invention and to eliminate any possible misconception about the functions of the system that my previous writing may have caused. The system itself is a lot simpler than what this prototype looks like because in the prototype I'm using 4 additional microcontrollers and their supporting components as well as 8 groups of extra wires only to display binary numbers to decimal for showing what is happening in the heart of the system. When displaying the numbers on the other side of the board, you may notice small fluctuations in the displayed numbers. The person in the art realizes that with the induction effects of so many jumper wires above the ICs, with the basic crystal clock generator, and with the basic frequency generators, which are used to simulate the frequency of speed and distance radars in the prototype, the system cannot be as precise as a pre-commercial or commercial system on a small PCB board which works with actual radars.